questions about anything before we get going? So I'm not sure if I mentioned what sections the test was going to be over next Wednesday. Basically 6.5 is the last thing that's going to be covered in that test. We might go one section further, but that's it. So basically what it's looking like is all day Monday is going to be a review section. But at least most of that class period will be. So look over the stuff that I posted on Canvas to kind of help you review. We can talk about that after we're done with the next section. So let's go ahead and get going. So one of the very last things you all talked about in Calc 1 was integration. And basically the way that was motivated is going to play heavily into what we do today. So here's a curve. I'm not telling you the definition, like the algebraic definition of this function. But think back to like the tail end of Calc 1, where you were approximating areas here. So let's call this function. If we call this function f, like f of x, and I want to find a value for the integral from 0 to 1 of this function, what are kind of the initial ways that you went about doing that? So I think before you learn how to do it exactly, there are ways you did it approximately, right? So yeah, so briefly explain to me what a Riemann sum is.
It's like chopping it in like sections.
Right. So if I wanted to approximate this, how could I get that done? Like you said, chopping it into rectangles. How many rectangles could we do?
Well, they're smaller.
Let's start small. Let's start with 2. So we'll divide this thing up from 0 to 0.5 and from 0 to 0.5 to 1, right? So when we chop this up using rectangles, basically what we do is, we kind of have the base length is going to be from here to here. But basically we have to choose one value for the height. How do we choose that? Or does it matter how we choose that? Right, so you can go from the left side. So if we went the left side, it would look like this, right? Have this very tall rectangle. And the left side over here, I think that would be, nothing, right? So if I did the left end point of the left side of the interval, I would just have, I think the left end point of that is actually the origin. But there are lots of ways to approximate these, right? But, before you had that tool available to you of actually taking antiderivatives to find integrals, this is kind of what you were left with, was using Riemann sums to treat these as rectangles. So the reason we're bringing this up now is because, like so far I've given you lots of functions that you can integrate. You can find an antiderivative of, evaluate that antiderivative of both endpoints, and you can find the exact area doing that. There are some functions that basically you will not have the ability to find an antiderivative for. So for those, we're going to use these approximation methods. So there are a bunch of ways to do that. Really, you have lots of choices, but we're going to talk about a few of the common ones. So I think, as you said, you can kind of choose which endpoint you use here. So if you use the left endpoints, we're still going to use like 5 rectangles here, but what's the difference between this one here and this one here, for example? Right, so I am basically, it's all about where I'm sampling. Am I sampling on the left-hand side of each little subinterval, or am I sampling on the left-hand side and the right-hand side? Am I going to get the same area for both of those? No. So because of that, even though for each one of these I'm showing you the same curve, where you sample makes a big difference. Where you sample makes a difference, and how many rectangles I decide to use is going to make a big difference. Let's say I stuck with right endpoints. How can I make this estimate closer to what it really is? I could divide it into more subintervals. So basically, you're trading. To get more accuracy, you're going to spend more time doing calculations or do more calculations. But really, when you go to like a definite integral calculator on your some of the more sophisticated like things like Wolfram will not do this, but if you go to like a TI-83, TI-84, and you ask for a definite integral, it's basically doing this. It's taking the function you gave it, the interval you gave it, and splitting it up into probably hundreds of thousands of rectangles and adding those together. And the error from doing it is going to be so small that it won't even show up in the digits on your calculator. It'll be that close to exact. So all the ones that we talked about here, the left. So I think before I even showed this to you, you mentioned left end, right end, and midpoint. Those are all based on rectangles, right? So when you do a rectangle, basically for each one of my subintervals, I have to choose one height, right, to stand in place for every y value inside that space. Trapezoids are a little different. So how am I making these trapezoids?
Start and end.
Right. So basically, instead of choosing an endpoint or choosing the midpoint, I'm using both endpoints, right? So basically, to get a little more accuracy, I'm going to get away from rectangles, which are incredibly simple, and find areas of trapezoids. Because the area of a trapezoid is something you know how to find. At some point, you probably had a formula memorized. We'll build that back up. But finding an area of a trapezoid is very, very similar to the way you find an area of a rectangle. So those are I think that covers all but one of the things we're going to talk about. But let's kind of get into it. So basically, for this section, just to kind of show the similarities and differences between each method, I'm going to integrate this. We're going to integrate this function several times, but we're going to vary the approaches that we use here. So first of all, let's cover this first. Is this an integral you could do exactly? So this is available to us using our more exact, like they're using our exact methods, which is that'll be the last thing we do to kind of show how good or bad these approximations are. But the first thing I want to do is I want to use left endpoints. I want to use 4 intervals. And I want to use that to approximate what this area is. It's not going to be exact, but I'm going to approximate it. So what are the different things we need to think about to do this? So let me do this. I'm going to draw a picture, and I do not pretend this picture in any way represents this curve with any kind of faithfulness, but it's just to kind of help me organize things. So 0 to 2. I want to make some rectangles. So how many rectangles do I need? 4. And where are they going to be? Like, where are they going to begin and where are they going to end? So 0 to 0.5 is a rectangle. 1, 1.5. So rectangle. Am I drawing them the right way? Okay. So yeah, I'm trying to use the left endpoint to represent the height for the entire interval. So I have my 4 rectangles, right? So now what do I want to do with those rectangles? Identify their length. So what is their length?
0.5.
Right. So for that length, just to kind of mimic some of the notation that is common in the textbook, I'm going to call that delta x. How did you find that? So we said 0.5. I don't think anyone. I mean, I didn't hear a formula, maybe you were thinking of one, but how do we know, like, where did we get 0.5?
0 to 2.
So 0 to 2,
Yeah, then divide that by the 4 intervals.
right? So basically, this is a formula maybe you've seen before. Actually, I am sure you have seen this thing in Calc 1, whether or not you remember it. So what do the B and A and N represent there?
0 to 2.
0 to 2. So basically, the upper limit of my interval, the lower limit of my interval, those are B and A. And the N is what?
4 intervals.
The number of divisions I'm going to take here, the number of intervals I want to use. So really the way Riemann developed this, there's no rule saying that you have to have the same delta x for every single interval. You can make them all different lengths, but that's what we're going to stick with. We want the delta x to be 0.5. All right, so how do we continue from there?
Plug in your x values that you're using.
Okay, so let's write this down. I want 4 x values. What are they?
It's going to be the left one, so 0, 0.5, 1, and 1.
Okay, so I want to stop there for a second. Because how many x values did I label on my graph up there? 5. So because I want 4 intervals, I do have to leave one out, and it's subtle which ones you're taking, which one you're leaving out. So want to make sure that we're okay with why I'm choosing those 4 x values. 0, 1/2, 1, and 1/2. How we doing? All right. What next?
Find what the value is.
Find what the value of what is.
Plugging in those x values into your formula.
Okay. So now that I have my x values, I want to find f of x1, f of x2. And while I'm writing these down, I might need some help. Or do all of these come out to be sort of convenient?
0.
0 is easy enough. 4/5.
1 over 1 plus a quarter.
1 over 1 plus a quarter. Okay, I agree with you. I'm going to do them as decimals because when you're looking at the homework and stuff, it's very typical that some of these don't lend themselves to nice fractions. 4/5 is nice. 13 over 128 or whatever goofy things you see in the web work that will pop up are harder to deal with. 1 comes out to be 1.
Yep.
Okay, easy enough. And finally, 0.923. I think that's okay. So we got our 4 values. Now what? Add them up. Let's be totally clear about what we mean by add up. What are we adding up?
0, 1.
So can I simply add these 4 numbers together? Right. Okay, so that's a couple ways to look at this, and I'll write them both down. If I'm trying to evaluate or approximate this integral, then I can do one of 2 things here, and they're really equivalent. Add all these things together, 0 plus 0.8 plus 1 plus 0.923, and then multiply that by my delta x, or I can represent it as, x1 times f of x1 plus x2 times f of x2 plus x3 times f of x3 plus x4 times f of x4. So both of those, they're equivalent things. It just depends on what makes more sense to you. I should not be using this symbol. I should be using. Can someone give me a final number?
6.
1.36. All right, so Now that we've done one of these approximate ones, how do we feel about it? Go ahead.
Towards that final answer, that 0.5, you're supposed to find your delta x.
Yeah.
Your percentage.
Yeah, so this, basically what we're doing here, these four things are areas of rectangles. Oh, I should not be putting those X ones there. That is totally not what's happening. What should I replace all these things with? Yeah. That's an absolute lie. So delta X. Yeah, that's why you had that question, because I was telling you something contradictory. But basically, these four things, these are areas of rectangles. Delta X is the baseline, and f of x1 is the height that I decided to. Basically, it's one of the y values I decided to pull out that curve and edit it. So I get the area of those four rectangles, add them together. I have a probably pretty bad guess, but a guess for what that interval is. Any other questions on this first one? Okay, so same function, same integral, but now I want to use right Riemann sums. So let's talk about it this way. What from this example am I allowed to reuse? Right, so the delta x I can maintain, right? So why is the delta x still the same?
Your integral is the same.
The integral is the same, and also the number of rectangles. So those two things are what drive delta x. What else can I keep?
X3 and X4 values.
Right. So those three values are going to be good. What happens at 0? I'm not going to use that this time. So let's use that to build up an arbitrary looking curve. 0, 1, 2, 0.5, 1.5. So now I want these points, right? So we said that we still care what f of 0.5 is, right? What f of 1 is, what f of 1.5 is, which, if I remember, are 0.81 and 0.923. What's my fourth point going to be? Because I do need 4 y values, right? Right, okay, so yeah, importantly, I want to know, 0.2. F of 2 is 0.8, right? So now I want so one thing we said, we wanted our x1, our x2, x3, and x4. Yes, we want those values, but now I believe they have become my x1, x2, and x3, right? And my new x4 is the far right end of this end. So any questions on the things that we kept from the first case, the things we changed? If we're okay with that, what do we do now? Add them up. So basically, this integral is approximately equal to delta x times all of my heights. Do I have the sum of all my heights? Which somebody will tell me is equal to 1.76. One piece of notation I want to expose you to is just that I know the book uses it and it'll show up in other places. Rather than write all these things out, we can do this. This is approximately equal to, what is this thing? So that's a capital Greek sigma. So I want to go from I equals 1. So basically counting from 1 up to whatever the number of subintervals I have, that's 4. And what am I really multiplying together, or what am I really adding together? I'm adding together all these products, delta x times f of xi. So basically, who in here has taken any kind of a computer programming or coding class? So I think about these things as loops. I tell you where the loop begins at I equals 1. Then I do this calculation, the delta x times f of xi. Then I count up to 2, do that calculation again, and add it to the old one. And I keep doing that until I reach whatever number appears at the top of that sigma. So you'll see me write both just because it's easier to write the sigma because I don't have to write out every single term of it. So how far off are we from our last estimate? Quite a bit, right? I think we're right, and I think we did it correctly in both cases. Just when you start changing parameters, you're gonna get wildly different estimates. Any questions so far? Okay. What about midpoints? Does anything we've done before still have like direct use here? Delta x should be the same, and let's be clear, why is that? Why is delta x still 0.5?
Your range hasn't changed either.
Right, so I still have the same overall interval, and I'm still dividing it to the same number of equally sized or equally long pieces. Does anything else I want, or does anything else I've done, can I recycle? Or is the answer to that question no? Okay, I think the answer is no. All right, so basically from this, we can use that delta x, but now what do we need?
You have to pick your.
Right, so now if I want 4 intervals, then if I'm doing a Riemann sum, that means I want, basically I have to, of the infinite number of x values I am using inside the interval, I have to pluck out 4 of them that are going to drive my approximations. So what are x1 through x4?
You would do pretty much 0 to 0.5.
Right. So basically, what's the average of the endpoints of that interval? 0.25. What should the next sample point be? 0.75, 1.25, 1.75. And what comes from all those? A bunch of decimals that I'm not going to try to do in my head because you all have calculators.
0.47.
The first one is 0.47.
0.47.
Okay.
And then 0.96, 0.98, 0.86.
Okay. Good. So, even though I can't use any of the numbers that I just used for the last 2 examples, basically, for a Riemann sum, this algorithm is pretty well defined. I'm going to take my interval, I'm going to split it up into equally sized or equally long pieces. That's what the delta x represents, of that length, that base length. I'm going to choose 4 sample points, or sorry, not 4 necessarily, but I'm going to choose a sample point from each one of those subintervals, and I'm going to see what the function tells me, like what the corresponding y value is for all those subintervals. So those things are repeatable even if I can't use all the same numbers. So I got my x values, I got my corresponding y values. Now what?
Add them all up and multiply them by
Right, so basically that is also repeatable. I'm not drawing the rectangles, but I've taken my 4 rectangles and finding their areas and summing those areas together. So the sum from I equals 1 to I equals 4 of delta x times f of xi. Which one of you will tell me the number for? Unless I beat you to it.
1.635.
1.635? How does that compare with what we've said in the past? So I think the truth is probably, it's somewhere close to our 3. So what do we say, 1.36, 1.76, and 1.635?
Average.
Is that the average of the first 2 things we did? It's close. I mean, there's no reason to expect it to be the average. Because even though I know the height, at the left, the right, and the middle, I don't know what the function's doing in between there. It's probably not a straight line. So might be close to the average, but it'd be a coincidence if it was exactly there. So that's all by definition Riemann sum. So basically using rectangles to find integrals or to approximate integrals. So any questions on any of the first 3 things we've done here? Because we're going to move into things that are Riemann sum like, but not technically Riemann sums. Okay. So now what I want to do is I want to use trapezoids instead of rectangles. So now that we're getting into a different geometrical situation, let me draw a sketch of some curve again. But I already talked about, so I briefly went over the way the trapezoid thing works. See how well I did. How am I going to draw these trapezoids on this curve?
Start at the left side and at the 0.5, like every half.
Okay. So yeah, I'm still using 4 intervals. I'm still doing the same function and the same lower and upper bound. But basically, instead of sampling one height for the instead of sampling only one y value of these intervals, I'm sampling 2 and joining them with a straight line. So a straight line there.
You'll need to get the slope.
Does that mean I'll need to get the slope? What do you think? Got 1 vote for yes. So we should probably remind everyone how to find the area of a trapezoid. What's the difference between finding the area of this thing? And all of our trapezoids are going to be like this. They're going to be mostly rectangular because they're going to have 3 right angles in them, but probably not the 4th, right? Or sorry, 2 right angles, probably not the upper ones. So obviously we know how to find the area of things like this. At one point, I'm confident you all knew how to find the area of trapezoids, but maybe that's evaporated. So let's talk about that. The thing that makes this area hard to find is this sloped side, right? What if we could replace this sloped side with something like, with a straight side? So I drew a rectangle on top of that trapezoid. Are we convinced that rectangle would have the same area as the trapezoid that I laid it on top of? Good. So now the question is, how do I find where this straight side is?
Side minus the left side, 5 by 2.
The right side minus the left side divided by 2. Why are you subtracting them?
To get the length of, to get the difference between the start and end point.
Okay, so that'll give you the difference. So let me throw some numbers on here. And we'll call the bottom of this 0. I'll call this 4. I'll call this 6. So the difference between them would be 2, right? Then you cut that in half. That would give you 1. What are you gonna do with that 1?
The start or subtracted from
Add it to 4, right? That would give you what? Okay, I promise. So that what he said will work. I think we can do something simpler, easier way. So, what would you expect this middle height is? If the lower height is 4 and the higher height is 6, what's the middle one?
5.
Are you sure about that? Essentially, what you're doing is averaging 2 numbers, right? How do you average 2 numbers? You add them, divide by 2, right? So, area of a rectangle is easy, base times height. Area of a trapezoid is what? Well, what did we do? We took the base, right? And we multiplied it by the average of the height, or the average of the heights. H1 plus H2 divided by 2. So basically, it's the length of the base multiplied by the average height. So you wanted to subtract them, I think. You got a couple of different formulas in your head. Yeah. Here's what I suspect happened. And pretty much, probably in a lot of your memories, the way you find the midpoint between things and the way you find the slope between 2 points, you probably learned them on the same day or very close to each other. One involves subtraction, one involves addition, and sometimes you confuse one for the other. But think about it as an average height. If I can find that average height, I can treat this as a rectangle. All right, so that's how we find the area of a trapezoid. We had a question a while ago from Maggie. Do we need to know the slopes of these trapezoids? Do we still think we need it? No, we don't need that. But here's what we do know. For the rectangles, how many y values did I need? I needed exactly one for every subinterval. How many y values do I need here? 2 for each one, and that's going to be a total of how many y values? It's going to be 5 because a lot of them overlap, right? Like for example, the right hand of trapezoid 1 is the left hand end of trapezoid 2. So I need to sample how many places? I need to sample f of 0, f of 0.5, f of 1, f of 1.5, f of 2. I think we have all these, right? So if someone wants to flip back in their notes and check out the math.
0 is going to be 0, 5 is 0.8, 1 is 0.92, 2.
Going off memory, I think it was
Yeah,
0.
you're right.
Okay, cool. So those are the points we need. What do I do with them then? So since this is our first time with trapezoids, and it's been a while, let's break these up into 4 different calculations. How do I find the area of the first trapezoid?
Zero, 0.8 divided by 2.
Right, so the base length is 0.5, but then we multiply that by the average height, which is 0 plus 0.8 over 2, which comes out to be 0.2. Point 1, I think. Oh.
Yeah.
Oh, was it 0.2 overall? Oh, I divided by 2 more times than I needed to. Okay, so 0.2. Let's do one more long form here. What's the calculation I have to do for area 2? So area 1, area 2. Those of you who are punching into calculators, tell me what you're punching in.
0.8 plus 1 divided by 2 times 0.5 was 0.45.
So 0.8 plus 1. So let me ask this question. Why is that numerator 0.8 plus 1?
Taking that, the left hand to not.
Right, so of trapezoid 2, the left-hand y value was set to 0.8. The right-hand y value is 1. I'm averaging them, so I want to add them together and cut that in half. And I multiply that by what? What do I multiply by 0.5? Right, so yeah, the data comes from the delta x. And did you say what that was? 0.45?
Yeah.
Okay. So now that we've gone through a couple of those, any questions on how to find those individual areas? If you have them, what are the last two?
0.48 and 0.43.
0.48, 0.43, which means, according to the trapezoid rule, this area is something like what? 0.56?
1.
Okay, that's better. So this is a little bit different from what we got from the midpoint rule, right? Should they have been the same? Because in both the midpoint method and this trapezoid method, we're averaging across an interval, right? But one subtle difference I want to point out is for the midpoint rule, what are we averaging? So like for the first rectangle from 0 to 0.5, what are we averaging? Go ahead.
You're averaging between delta and then you're sampling from the actual function.
In the midpoint rule, in the midpoint method?
Yeah.
Okay, right. So yeah, basically we're sampling, basically in one of these we're averaging x values. We're averaging the sampling point. In the other one, in the trapezoid rule, we're sampling at both points and averaging that. So because of that, they might be similar, but they should be slightly different. How are we doing so far? Okay, any questions so far? All right, last one I want to show you is Simpson's rule, and there's a long derivation for this that I think there are better uses for our time to go through, but basically here's the way the Simpson's rule works. Oops, sorry. So first, kind of drinking notation. You don't have to copy this down. It's on Canvas, but take a minute to study it over, and we'll talk about it. Basically, what this, mathematician, I can't remember his first name, Mr. Simpson came up with is that you can approximate an integral basically by trying to take whatever curve you're trying to integrate underneath and treating it like a polynomial. And in all this investigation, he came up with these coefficients. So I believe strongly, actually, you know what? This is not given to you. And I wish I had a good reason for you why, but it's not. So let's talk about how you can have a good sense of remembering it. So how does this thing work? So you're doing something with the base length here. So in all the methods we've used so far, you're just multiplying by delta x, purely delta x, right? In this method, I'm taking the third of that. And then what am I doing on the inside of this thing? Does anyone notice anything about the coefficients of all those terms on the inside of that bracket? Any patterns jumping out at anybody? Go ahead.
You alternate multiplying them by 4 and 2.
Everywhere? I do see the
Except the first and last term.
Right, so the first and last are always what? What are the coefficients on the first and last terms? Those are always unity, those are always 1. But then what do you do with every other term? 4, 2, 4, 2, 4, 2. So here's one thing I do want to point out is that this thing looks different if I have an even number of terms and if I have an odd number of terms. So let's look at a couple. So let's say that I have one of these n equals 3, now let's do 4. And one of these n equals 5. Then what are these coefficients going to be? So we said that we are confident about the first one and the last one being, those are unity, right? Those are coefficients of 1. By the way, how many sampling points am I going to have? It's n plus 1. It's not equal to n. So one thing I do want to point out in the way that I type this out is that it goes from 0 to n. How many numbers are there between 0 and n? And 1 more than n. So we have n plus 1. So I'm going to have 5 terms in here, right? So if n equals 4, then I'm going to have 5 terms in here. So I know like the n's have a coefficient of 1. And if I go in 1 from each end, those are coefficients are going to be 4. Give myself an plus 4 f of x3. So for me, doesn't necessarily mean it's going to be true for you, but for me, I think it's easier for me to go from the outsides and build your way inward because it looks like it's an alternation, but it's not strictly speaking an alternation. How many terms are left that I haven't written down? Just the 1, right? And what's its coefficient going to be? 2. So 2 times f of x2. So in that case, when I have an even number of n, that looks like an alternation. But what happens if I build it up for n equals 5? Still f of x not. What's the last term for me this time?
That's 5.
F of x5. If I go 1 term in, what do I get? For f of x1 or f of x4. How many terms are missing here? 2. And what are their coefficients going to be?
2.
They're both 2. So because of that sometimes it looks like it's purely alternating. Sometimes you get these duplicated 2s.
It was an n of 7, so if it goes 4, then 2, then it would be 4 we're building inside.
Yeah. So like if you have an odd number, so basically if n is an odd number, your very middle 2 terms are going to have the same coefficient. If the n is even, it's going to be purely alternating 4, 2, 4, 2, 4. Always ending. No, so that's what Caleb was just saying. If this was n equals 7, your middle terms would be 4s. Because so I don't think I have enough room to write it, but let's imagine it.
Try n equals 3.
That's even more efficient. I can do that. Sometimes I need you to remind me what odd numbers look like. So if I do n equals 3, 1/3 delta x. First term is f of x naught, always. What's the last term? Those are always coefficients of 1. What's in the middle here? 4 times f of x1. And so basically if I go left from x0, then I get 4 times f of x1. What if I go one term back from f of x3? It's 4 again.
It's like you get it.
Yeah.
You get it.
Right. So, and that's one way to. I think that's the way that's why I prefer to think about it that way, because the only thing that's like really repeatable in my eyes here is the fact that the last term has a coefficient of 1, the first term has a coefficient of 1, and then if you go inward, those both have 4s, and then okay, there's only one left that has a 2.
But it's always 4s and 2s as you go.
It's always 4s and 2s. So, like I said, if you want to yell at somebody about me not putting this as a formula on the test, I'm not the right person to yell at. You can yell at me about whatever you want, but sometimes it won't make a difference. So hopefully that helps kind of organize this and the web work, which I swear I will promise to try to remember to open for you after class today. So did a lot of talking about the Simpsons rule. We didn't use it, so we'll start with that on Friday. Only got like 2 minutes left. So basically, did I tell you what the test covers? What sections? 6.5 actually. So we will probably cover 6.6 before the test happens, just because we're there. So basically, here's what's going to happen on Friday. We're going to finish 6.5, which should take just a few minutes. We'll get into 6.6, and I don't know if we'll finish 6.6 on Friday, but basically on Monday, basically worst case scenario for you, most of Monday will be a review session. Best case scenario for you, all of Monday will be a review session. I'll kind of figure out where we ended up and what makes sense to do. So because of that, start looking at, if you haven't already, start looking at those review materials on Canvas and figure out what you need to polish up and what kind of things you want to talk about in class. Any questions? All right. I do have office hours today at 1:30.